Okay, in a previous video, we talked about what we were up to was finding the mean square value of the output. It's a random process. Uh, that's a result of sending a random process input through a stable system. And we're talking about the steady state mean square value. And we had three ways to compute it. And what I want to talk about more is the method that uses this relationship. And we took it on faith. Someone had derived these formulas for it. You know, your mean square value in steady state will be some I sub n, where n is the order of this polynomial d of s. So if it's first order, second order, third order, and I think we never even got to third order in my course. The worst we had was second order. And I did one example of that. So I don't want to go through this again, but what we're doing here is called spectral factorization. We have to split this power spectral density up so that we get this C of S over D of S, and all the poles and zeros are strictly in the left half plane. That's splitting up. To do it that way is called spectral factorization. And that's what we did. So I want to talk some more about that. And we'll do another example. Here's our system. It's the transfer function. And we have the autocorrelation function of the input. Our job is to find the steady state mean square value. Well, we're going to need a formula that's like, it's going to look like this, where is it? It's going to look like this. So we're going to need the power spectral density of the input, and that's just a table lookup, a Fourier transform table lookup. So this is the power spectral density, or the Fourier transform of this autocorrelation function. Now we need to do spectral factorization of this guy. Step one is to go from omega to S. Excuse me, and S equals j omega. So if I square it, I get S squared equals minus omega squared, or minus S squared equals omega squared. So that's switching to S. And now I want to split this up. The numerator is easy. It's just a constant. So what's in each of these numerators is just the square root of this thing. And the bottom, you can spectrally factorize this one. Convince yourself if you multiply these two guys together, you get this. So now I have G of S times the G of minus S times these two guys. And this guy's, the denominator's roots are in the left half plane, and this guy's denominator's roots are in the left half plane. So this is the guy I want. This is my C of S over D of S. So we'll multiply the numerators, multiply the denominators, we get this. Then we can identify all these C's and D's with terms here. C1 will be 0. There's no S over here. C0 will be this whole numerator. D2 is 1. D1 is this middle term here. And D0 is this term over here. I have all the C's and D's. Put in the formula. I put them in and I simplify. And here I get the steady state mean square value. Things you're going to have to do in finding either the C or the D. If it's a 0th order polynomial, that's easy. Just take the square root of whatever it is. And by the way, your polynomials in omega are always going to come in even powers of omega. You're not going to have an omega or an omega cube. It'll be a constant, an omega squared, or an omega to the 4th, or to the 6th. And here's formulas that are just derived by simple algebra, how to factor these guys. If it's like this, it just factors, you want this term, S plus an A. This A is just going to be the square root of this term on the right, and it'll be greater than 0. For a fourth order polynomial, and it's going to look something like this generically, you want this guy where A and B are both greater than 0. The B is, again, just this right term. It's the square root of whatever that right side term is. And then the A is this Q squared plus 2 of whatever your B is. Anyway, we'll just write them down, use those formulas. And here's an example of that. Here, we're given the output power spectral density, but we need to do some spectral factorization of this thing. The job is to find the mean and the mean square. Since there's no Dirac delta function in this, we learned many videos ago that means the mean is 0. So the mean square, we have 3 ways to go about it. Here they are again. In this case, finding the inverse Fourier transform of this thing is not in most Fourier transform tables. Taking this integral of this guy, again, that's not in many tables of integrals. The easy way to do this one is this spectral factorization method, these I sub n formulas. So let's do that. We're now just doing an example of using those little formulas now. Here's the example. The numerator is a constant, so that's going to break up easy. You just take the square root. The denominator is a polynomial. We want it to end up looking like this. It starts out with a fourth order polynomial. We want it to get it down into a quadratic. And we use the formulas on the previous page. The B will be the square root of this 1. So it's just 1. And the A was, I think it was, well, the middle term is, there is no middle term. There is no omega squared term. That's why we have the 0 here. And then plus 2B. So the A here is square root of 2. So we have our C of S over D of S, and there it is. Then again, you just identify all these C's and D's of your I sub n formula with these guys. There's the formula. You plug in what all the C's and D's are, simplify, you get 1 over square root of 2. And that was the mean square value, and this was the output steady state. We could use that same idea of spectral factorization to do this thing called a shaping filter. And what we do there is we're going to put white noise into a system to get a desired power spectral density output. We want to know, what should that system be? What should the transfer function be? So we have this formula now, because input power spectral density is white noise, so it's just 1. And we'll say in this example, we want this output power spectral density. Well, we do the same kind of spectral factorization. Our C is going to be the square root of this numerator, which is 4. And we want to break this guy up again, just using the same formulas we just did. It's going to look like this. Our D is going to look like this, and we use those little formulas again. The B is going to be the square root of whatever this is, which is 8. And the A is going to be, well, the omega squared term is 0. That's that 0. 2 times B, and that's a 4. And we get this. And that's the transfer function we want. Convert white noise to give an output with this power spectral density. And that'll be it for this video.